Today we're looking at perpendicular and angle bisectors. Our objective is to prove and use theorems about perpendicular bisectors and angle bisectors. Our first theorem we want to look at is the perpendicular bisector theorem, and we're going to prove this in example 1. In a plane, a flat surface, if a point is on the perpendicular bisector of a segment, so for example we have C here, then it is equidistant from the endpoints of the segment. So what that's saying is if this line right here makes a 90-degree angle with this line segment AB and it's right in the center, then it's going to, these two sides are going to be exactly the same length. The converse of the perpendicular bisector theorem is if you have a plane and the point is equal from the endpoints of a segment, then it has to lie on the perpendicular bisector. So this just says the opposite is the converse of the perpendicular bisector theorem. We're going to prove the perpendicular bisector theorem. We're going to do our 2-column proof. We have our statements and our reasons. We are given that CM is perpendicular to AB. That upside down T just means perpendicular. And CM is going to bisect AB. So bisect means it cuts something in half. Now we have this line right in the middle, the perpendicular bisector. It cuts a big triangle into two smaller triangles. So we have CM is going to be congruent to CM because of the reflexive property. Now, as you can see, we are just going to be proving these two triangles are the same so that we can show CA is congruent to CB. Well, the measure of angle AMC is equal to 90 degrees and the measure of BMC is equal to 90 degrees. The reason we know this is the definition of perpendicular. This is a perpendicular bisector. Since both AMC and BMC are equal to 90 degrees, they are equal to each other. On this line, you can put all right angles are congruent, or you can just put transitive property. Either one of those is fine. We also need to show that AM is congruent to MB. And the reason those are congruent is because CM bisects AB. So the definition of a bisector means that those would be equal on both sides. So since we have two sides and an angle in between, we can say a triangle AMC is congruent to triangle BCM, and that would be by side angle side. Now, since these two triangles are congruent, all of the parts of the triangle have to be congruent. So CA is going to be congruent to CB because of corresponding parts of congruent triangles are congruent. On example 2, I have MO is equal to 7, so NM has to equal 7. And the reason for that is because it is on a perpendicular bisector. Example 3, AM equals 5, AC equals 6. So we're finding BM and BC. So since it's a perpendicular bisector, CB has to equal 6 and MB has to equal 5, or BM has to equal 5, and BC is equal to 6. Example 4, we are seeing if we can use the perpendicular bisector theorem to find CB in the diagram below. So we've got to be able to tell, is that congruent? Well, perpendicular bisector theorem says that it has to be on a perpendicular bisector and it has to be equidistant from the endpoints. Now, it's right, but we don't know if it has cut it in half, if it's bisected. So if I were to draw a triangle that had a 79 on the left and it's very long on the right, I could still have all of the things here. And so this would not be congruent because we can form a triangle where it would be longer because it doesn't show that it's a bisector. On example 5, we are looking at the diagram and seeing which ones are equal. So 17 is obviously equal to 17, so AB would be congruent to CB. It's perpendicular and it's equidistant from both sides, so the inside has to be congruent. So AE has to be congruent to CE. And since D is right on that perpendicular bisector line, it also has to be equal. So AD has to be congruent to CD as well. Okay, we have some more theorems. We have the angle bisector theorem. So remember, a distance from a point to a line is the length of a perpendicular segment from the point to the line. So if we have a point on the angle bisector, then it's going to be equidistant from two sides of the angle. The converse says if a point is on the interior of an angle and is equidistant from the sides, then it has to lie on the angle bisector. We're going to prove this in example 6. We're going to prove the converse of the angle bisector theorem. So we are given that PB is perpendicular to AB and PC is perpendicular to AC. So PB and PB is also equal to PC. So we know that by the reflexive property, AP is congruent to AP. So since we've got these two triangles that are congruent, we have a right triangle on both of them and they have a hypotenuse and a leg. These two triangles are congruent by HL. So triangle ABP is congruent to triangle ACP. And since we have corresponding parts of congruent triangles are congruent, the angles have to be congruent. BAP has to be congruent to angle CAP. And since those angles are congruent, AP has to be a bisector of angle BAC, which is what we are trying to prove. Example 7, we've got, if we have angle bisector there, those two sides have to be equal. 4x minus 5 has to equal 23. We add 5 to both sides of the equal sign. So we have 4x on the left equals 28. We divide by 4, which is the opposite of times, and we get x is equal to 7. On example 8, we have these two angles are the same because it is equidistant on both sides of the angle bisector. 2x plus 5 has to equal to 3x minus 17. I subtract 2x from both sides of the equal sign. 5 equals x minus 17. I add 17 to both sides of the equal sign, and I get x equals 22. But I'm trying to find the measure of both of these angles. So if I take my 22 and plug it into 2x plus 5, I get 44 plus 5 is 49 for the top angle. And let's just do it for the bottom angle just to make sure we're correct. 3 times 22 is 66 minus 17 gives us 49. So both of those would be equal. They'd both be 49 degrees. So number 9, we're looking to see if this diagram allows us to conclude that QS bisects angle PQR. So if you look at this, we do not know if PS and SR are perpendicular. So they need to be perpendicular there, so no, we don't know.